Hmm. Hmm. Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone. Before we start, does anyone have any questions? Things clear? Okay.
Like in the third lecture, we say that an Euclidean space is Rn.
The Euclidean spaces are,
But in the last lecture, we say that we need to do a chart of an Euclidean space that works in Rn.
Yes.
So what's an Euclidean space?
Yeah, okay. So what we used as last time is Euclidean space as an abstraction of what we're living in, and then we called it E, and then we called a chart of it, then that goes from that space to Rn. Okay, this is the chart that you use it to represent it, that space with numbers. This already makes it Rn. So this already makes it an Euclidean space. So in general, so the term Euclidean space usually refers to Rn in that sense. Okay, so they are one-to-one. Okay, last time when we were talking about relative poses or of rigid bodies, we just distinguished that this is abstract and this is a representation of it in Rn. Because it's not always, again, the Rn you're always used to is X, Y, and Z, right? Or you just put tuples of numbers, but these are charts. This is a choice of charts on the Euclidean space, which is Rn. So you can think of, this is something we didn't do, to think of Rn as a manifold itself, and then try to represent it in charts. One chart will be the identity. So take X, Y, and Z as the Cartesian coordinates. Another way is to look at it as polar coordinates, right? You don't have three real numbers. You have two angles, for example, and one distance. So this will be spherical coordinates, polar coordinates in 2D, and spherical coordinates in 3D. You can have Cartesian cylindrical coordinates where you have one angle and two distances and so on. So these will be different charts for the same space Rn. So this is why we just differentiated between the abstract one and the one which is Rn locally in the chart. Okay, hopefully that answers your question. Any other questions before we start? Okay, so today we're going to be continuing on topic number 2, rigid body modeling. And as a recap of last time, so we said that most robotic systems will be considering will be rigid bodies connected together by joints. It's essential or fundamental to understand how to model a rigid body and how to connect these rigid bodies together. And this is how we're going to be building up complex models, or so dynamic models for complex robotic systems. We said the configuration space of one rigid body. So everything we're going to be doing in topic number 2 is one rigid body, just to understand it very good. So one rigid body, so one rigid body, the configuration space of it is the special Euclidean group in ND. So when N here would represent 2D and represent 3D, so we can represent the configuration of rigid bodies in a plane or the configuration of rigid bodies in space in 3D. We said that one element of this special Euclidean group is the pair R and psi. R is an element of SON, the special orthogonal group, and psi is a translation vector. We said that this is a group because it has a group operation that would take two elements of this and give us another one. And this was how the group operation was defined. It has an identity element and it also has an inverse element. In the homework, however, again, just followed the advice and did the problems in the homework before this class, then this should be clear to them. Where do these operations come from? Again, by just looking at composition of different isometries. If not, you can go back to the homework problem. You're going to find the proof of this and the intuition behind it, that it's mapping points in Rn to Rn. Then we said, instead of working with this pair as one element in SON and one element in Rn, we can combine them by going up one dimension higher, and this is using some tools from the projective geometry. And then we can look at what are known as homogeneous transformations, which is simply an n+1 times an n+1 matrix. It's not any n+1, any n+1 times n+1 matrix. It has a very special form in this way, such that it's constructed in this way, such that when we do matrix multiplication, when we do a matrix multiplication between two of these homogeneous transformations, we recover the group operation on SEN, the one that was with the pair R and psi. And when we do the inverse of this 4x4 matrix, we get this very special form where the inverse of the rotation part is just the transpose, and we get this is the new, like the translation vector going back from after taking this H like edge transformation from the beginning. We said that SEN has a structure of a Lie group. We said that the Lie group is a manifold and a group at the same time. It's a manifold because this inverse operation and this group operation are smooth. Okay, you don't need to prove it, but okay, we're just going to start from there. So we're going to assume it's a smooth manifold, so infinitely differentiable. We don't need to worry about any orders of differentiability. This is usually the easiest thing to do. And SON itself is a Lie subgroup. And together, SON and RN make up this group, which is SEN, when we say that this notation represents the semi-direct product of SON and RN. It's not a direct product. It's not like that we take rotations alone and we take translations alone. It's a semi-direct product because there's this coupling between rotations and translations. Now about kinematic modeling of a rigid body. So the kinematic model represents the motion of bodies in a robotic mechanism without talking about forces and torque. So this is what kinematics, what do we mean by kinematics? The alternative of a kinematic model is what's known as a dynamic model. In a dynamic model, we start looking at what kind of forces and torques are applied on this body to generate this motion. But for now, we only look at kinematic relations, which means the relations, the geometric and the temporal relations between position, velocity, and acceleration. Position and velocity and acceleration in the general sense between two frames that are moving and rotating with respect to each other. And you can have this, in general, you can have this scenario where you have your robot arm that consists of a moving base, consists of some manipulator putting on it. And this is what we mean by a floating base manipulator. The end effector is usually the most important point on this robot because this is what's used to manipulate the environment or to interact with it. We have some sort of body that we're interested in holding or grasping or doing whatever. We have always a stationary frame, and then we have some sort of motion capture system or some camera that, again, it's measuring some information. It's very important here, and this is one of the assumptions we mentioned last time, is that it's very important to have a stationary reference frame, because this stationary reference frame defines usually your home configuration, your home pose, the relative position, such that when we say identity matrix in terms of 4x4 identity matrix or a 3x3 identity matrix, then we mean that these frames, these other frames, coincide with this reference configuration, with this home position, with this stationary frame. Okay? That's why it's very important to have the stationary frame. And for those who went into the reading material, they'll find that we started in this reading material, it was mentioned generally what the rigid body is without talking about this reference frame. And then at some point it was introduced as a postulation. And then we needed to that we can talk about relative poses. So in the end, so the bottom line is that there isn't anything called position of a rigid body or a pose of a rigid body. There's always the pose of a rigid body relative to some other frame. We're always talking about relative poses and relative orientations. Now, some important notations. We're going to fix this notation once and for all, and then we're going to be using it for the remaining part of the course. It's a little bit different from what's in the one of the books that we're going to be relying on, the main textbook of the course, which is the book by Lynch and Park. But again, I'm going to try to not too much to deviate from this notation so that when you go to read the book, it's not a big of a deal. A frame. Each one of these Euclidean spaces, what we discussed about last time, these abstract spaces will be associated to some coordinate frame. It's attached to it. And we're going to either interchangeably represented by psi of I or curly brackets of I. So when we say this or that, we mean a frame that's attached somewhere. It can be stationary, so not moving, or it can be moving all over the place. So, and then if it's moving all over the place, usually we assume it's attached to somebody, and this body is the one that is moving, and this frame is moving with it. We assume all frames are right-handed and the axes are orthonormal. This is just to make our life easier when doing some calculations. We don't assume that the body fixed frame, and this is an important point for those who already have some background on homogeneous transformations. We don't assume that the body fixed frame is specified in any special manner. It can be arbitrarily specified. So there is no such thing as DH parameters. Who's familiar with that? Okay, DH parameters. Okay. If you know the term, you know it. If you don't, forget about it. Okay, so there are no specific form how we represent these frames relative to each other. When we say it's attached to a body, so if this is the body, it's attached to it anyway at any point, and it just rotates with it and translates with it. That's it. Okay? So no assumptions, and this is what we mean by a body fixed frame can be arbitrarily specified on that body. The orientation of frame I with respect to K, the relative orientation of these two frames is given by the rotation matrix I with respect to K. It's an element of SO3. We're going to be assuming everything is in 3 dimensions. 2 dimensions are just a subcase of that. We can look at it at like an assignment or so. But again, everything, whenever we say SO3, definitely holds for 2 dimensions. At some point, some of the dimensions, some of the calculations, abstractly they are the same, but numerically they look different. But in general, everything we say on 3 dimensions holds for 2 dimensions. The relative orientation between a frame I and a frame K is given by the rotation matrix I, R I down K up. The displacement of the origin of I expressed in K is given by psi I down K up. And combining these 2 pieces of information, we're going to get the pose. So when we say the pose, we mean the combined orientation and displacement of this frame with respect to that frame is given by this element of SE3. Wait a second. Okay, in this configuration, if I, again, just as an intuitive question, when we say that the relative configuration, for example, between frame C and frame A, sorry, the relative pose between frame C and frame A is the identity. What does that imply? They are the same. So they have the same what? They have the same orientation, right? And they are, so their axes coincide exactly. And what else? What? There's no reflection anyhow, because we already canceled that out when we looked at the determinant of R is equal to +1. So we already removed reflections. What else? Exactly the same point. So the origin of the frame C is the same as the origin of frame A. So this is what an identity element means. And you see, it doesn't make sense without having this reference configuration in the first place. Okay, so always keep that in mind. Another question is, if I know the relative pose between frame I with respect to frame K, what would be the relative pose of frame K with respect to frame I? The inverse of it, and then this inverse is not the transpose. So the inverse of the rotation matrices was the transpose, but the inverse of the homogeneous transformations was not the transpose. But the homogeneous transformations, it has 2 components, a rotation part and a translation part. The rotation part of K with respect to I is the transpose of I with respect to K. And the translation part of K with respect to I has a coupling between the rotation part and the translation part of I minus K. Okay, so it's not just the minus of the distance. So if I go in this direction and I come back with the same orientation, it makes sense. I go positive 5 meters and I come back minus 5 meters. So that makes sense. But if I'm rotating and translating at the same time, so I need to invert back this rotation I did before going back the minus. So this is the intuition behind. And you can always try to convince yourself with some examples, hopefully in the homework, inshallah. There's a question here. If the body itself is rotating, this is what we mean by a body fixed frame. If here, for example, we say that the frame C is attached to the end effector, so whatever orientation the end effector takes is the same orientation as the frame C attached to. This is what we mean by a body fixed frame. If it rotates always with it. Okay. Clear? Any other question? If we're given the relative pose of frame I with respect to frame J, and then we're given another piece of information of the relative pose of frame J with respect to frame K, then the group multiplication of SEN does the following. It relates the frame I with respect to frame K in this manner. Okay? And remember that the group operation is not commutative in general. So SEN is not an abelian group in general, which means that HI with respect to J pre-multiplied by J with respect to K is not the same as I with respect to J post multiplied by J with respect to K. Okay, so the order matters here. And you can read this always as the following. So this is I with respect to J and this is J with respect to K. So the J cancel out. So this is a nice way of, and this is also one of the reasons I choose this notation here. It is a bit different from the book so that you can cancel these out in this one. Okay, the book would use all of them as subscripts. So it would in the book you're gonna find this is written as IJ JK, and this is IK. Okay, again, it's just a taste. I prefer this one. The book also uses for homogeneous transformations uses T. Okay, as in transformation, not homogeneous transformation. I use here H because I don't want to use the T at all because the T is used in several yeah. 7 places and several meanings. So I don't just want to remove the T completely. Okay, so now if you're given, again, and this is something you face all the time, or if you're working in a practical example, usually you know the configuration, for example, of this camera with respect to the A frame. I know the configuration of the C frame, which is the end effector with respect to the body, by knowing the joint angles in between, something we're going to look at later, inshallah. And then I ask myself, if I have the C with respect to the camera, and this is what I get as an information or a measurement, what is the C with respect to the stationary frame? And then you can use this like chain rule in terms of the indices to clearly find out any transformation you want. And you see it's as simple as matrix multiplication. There is no fancy, you don't need to worry about rotations and translations going back and forth. It's just matrix multiplication. And this is one of the reasons why we did this, okay, going up 1 dimension and looking at fourth dimension in this case, matrices. Okay, any questions? Again, all of this will be clearer with examples in the homework, inshallah. This is important, and this is the topic of today, which is velocities. So everything we talked about is position, right, or displacement. We have translational displacement, translations, and we have rotational displacement. Now, if you have displacement, you always have velocity, right? Because we're going to look at kinematics. And kinematics is simply the relation between position and velocity. And of course, the first thing comes into your mind that the rate of change of position is always equal to velocity. That's not the case. No longer, okay? So the rate of change of position is something, and velocity is something else from now on. This will be clearer later on. We're going to introduce several types of velocities. And the velocity always has 3 indices. You can always talk about the velocity of one frame with respect to another frame expressed in a third frame. So there are always 3 indices, I, J, and K. And they're always represented like this. So index down means the velocity of this frame, or equivalently, the body that's attached to this frame. So if I have a body fixed frame on a drone, then it's the velocity of this drone. With respect to what? I always need to specify the velocity of the drone with respect to something. And this is the J here. The velocity of I with respect to J, the velocity of body attached to I with respect to whatever frame J we have, which can be something that's attached to another body or that's something that's fixed. And I can express it in any third frame. And that third frame intuitively can either be I, J, or any other thing. So always keep that in mind. It's a rule. Okay, don't forget about it. What? You always have 3. You always write them in 3. And then you can, again, the K can be I and J in this case. But that's still, but then you read it as follows. Omega I, J, I, for example, is the velocity, angular velocity of frame I with respect to frame J expressed in frame I. Omega I, J, J is the angular velocity of frame I with respect to frame J expressed in frame J. And I can have omega of I with respect to J expressed in frame K. That's completely natural, okay? In this way, you're not going to make any mistakes. So, and Zayad, question?
What does it mean expressed in a different in K or so?
Very good question. If you're all now in this class, you're all fixed. So what is the relative velocity of each one of you relative to another? 0, right? So it's a trivial case. Okay, now another case is that Farouk starts to move around, and I'm at the same time, I'm also moving, okay? So he has a velocity of himself with respect to the ground, so it's no longer fixed. And I'm also moving at a different velocity. I can look at my velocity with respect to Farouk, and I can express this abstract notion in any other frame, either from this frame or that frame or this frame or that frame. You all see the velocities differently. Abstractly is the same, but you represent it with different numbers, okay? So choose a frame that looks like this. Yep, like this. Okay, Yusuf did it. Okay, frame like this. Okay, so this is your positive X. Choose a frame that looks like that. This is your positive X. Okay, so am I moving now positive X or negative X with respect to you? And you? Negative. You see? So this is what I mean. So the numbers are different. My motion is the same. I'm moving with respect to the ground. You're looking at me with respect to the ground. But here it's positive number. Here it's a negative number. Okay, so these are the different frames. And now I didn't take into account that you're also displaced and maybe you have different orientation. So again, you're gonna maybe get some component in X and some component on Y and blah, 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 blah. So this is the intuition grant.
These are observers?
Observers, absolutely. This is what the observer means. Yeah. In this setting, not in a general mechanics, which is also related to mechanics, but the term observer is also used in wild places, okay? Also in quantum mechanics. This is not what we mean, okay? The SO3 now, okay, so now our position or our configuration variable is a matrix. And now we want to represent the rate of change of this matrix. Okay, so this is the first thing you think about. Okay, I have some position variable and I take the rate of change of it. But what does the rate of change of a matrix mean? Okay, now this is where we look at the geometric structure of it. SO3 and SE3, they have a Lie group structure. And this is what we're going to be using to try to understand what does it mean to have the time derivative of a matrix. How can we take the derivative of some function with respect to a matrix? How can we do all of these weird stuff? So the abstract notion of a rigid body that's rotating, first we're going to be looking at rotations first. Then we're going to extend that trivially to translations and rotation at the same time. Because again, because of this idea of looking at it abstractly. So the Lie group SO3, if we represent a curve on it that looks like this, then this corresponds to different relative orientations. Okay, we have here an identity element. Somewhere there's a very special point on a Lie group that's called the identity element. In general, a manifold doesn't have that. A Lie group has this. That's why if you're studying a problem that has a manifold structure, you're in bad luck compared to one that has a Lie group structure. Let me give you an example. If you have the surface of the sphere, where is the special point called identity? Nowhere. But if you have the manifold that's called SO3, we have a very special point that's called the identity, right? Because this identity, when I group it with any other element, what do I get? I get the same element, right? So that's why it's an identity. It doesn't change anything. The same also for a vector space. The vector space also has a special structure because it has the zero element, has the zero vector. If I add something to the zero vector, what do I get? The same thing. So you see, these have a vector space has this very special element. Lie group has this special, or in general, a group has this special element, the identity, but a manifold in general doesn't have. We have a Lie group structure here. So we look at this curve. And at any point, so this curve is parameterized by t. So it's a curve, we call it gamma r, that is a map from some interval that as a subset of r and goes to SO3. We take up like a parameter t, and then we go the curve at that parameter, we define it as r sub t. And usually you're going to find this written in other places, r of t. Okay, so have you ever seen a matrix that's a function of time, or a position variable that's a function of time? This is when we start talking about a manifold. Because if we are only talking about the rotation matrix, so one rotation matrix and another rotation matrix, there is no time involvement. But once I have as a function of time, then I'm starting to talk about the differentiation with respect to that time or that parameter and so on. Okay? So this is usually some other notation that people write as a r of t. Okay? But r of t, what they simply mean here is they call this curve by r. Okay? So this is the reason why we call this curve gamma r and not r, so that you know whether it's the point that's on the manifold or the name of the curve itself, okay? The name of the map. Now, what we're going to be doing on the board now for the rest of the lecture, inshallah, is how can we represent the rate of change of this r, the rate of change of moving along this curve, which in the end, we remember what we discussed last time, it's a tangent vector at the tangent space to the manifold at this point r. So how can we represent this rate of change of this matrix to what's known as the angular velocity, the one that you're used to. Okay? So the angular velocity of one frame with respect to another frame expressed in a third frame. So this will be what we're going to be doing for the rotations. But then we're going to be going to the SE3. We're not done yet, so this is just an outlook. Okay. So, question.
The mapping takes me from R to SO3.
Yeah.
But the point T, it's within the manifold SO3 or within this set of SO3.
T lives in this space, in this interval. So T is a value. This interval can be something, a closed interval from 0 to 1. So at time can be equal to 0 or up to 1. So time equal to 0, for example, would be this point here. And time equal 1 can be that point here. But these points here on the manifold, they are R. They are rotation matrices. Okay, so this is how you think about it. At every point in time here, you get different configurations. You get different orientations.
Within this set SO3 or this group SO3.
This group SO3 is the group of rotations. Right? So every point here corresponds to a 3x3 matrix. Corresponds to a rotation of some frame with respect to another frame. Okay. So always think about it this way. So here, and this is something very important. This is the benefit of thinking abstractly. R is what? Is a 3x3 matrix. You all agree? Everyone agrees? What about R dot? Is also a 3x3 matrix. So, but in this picture, R, we think about it as a point on the manifold. And R dot, we think about it as a vector that lives in some vector space. This vector space is called the tangent to SO3 at the point R. Okay? So this is where vectors, and not everything is vectors, comes into place. Always keep that in mind. Keep that picture in your mind to go back and forth. This picture is exactly the same that we have when we go to SE3. We also have here, if I have relative changes between two frames, then this homogeneous matrix is another 4x4 matrix that lives in SE3. So it's a point on this, and it's another manifold, SE3. And also there's a curve there parameterized by T, and everything is the same construction. Okay? Of course, it's a different manifold. Okay? It's a different Lie group, but the construction is the same. So if there is anything that holds for Lie groups in general, it will hold for SO3 and SA3 at the same time. And this is what will make our life easier, inshallah. Now, some questions to think about. If H, which is a point here on SE3, represents the combined orientation and displacement of some rigid body with respect to some frame, can we represent the angular and linear velocity into one combined something, one combined variable? That's something to keep in mind. Is that possible or not? The answer is yes. There is a variable that represents, just as H, while it represents rotation and translation at the same time, there is another variable that will represent angular velocity and linear velocity at the same time. This variable will be called the twist. The second question is, how do we represent the rate of change of H with respect to this new variable that will be called a twist? So this is what's up next. Now we go to the board, and there will be a lot of writing today, okay? So I'm gonna go a little bit fast, and if there's anything, stop me if needed. Any questions before we start? Okay. Let's start by having the picture that we drew. First, we're gonna look at the Lie group structure of SO3. So this is the first thing. So this is SO3. And by the way, there was another, last time, I think, a question, I think from Julio, that he asked about whether this picture is SO3 is actually like a flat, like a unbounded manifold, or is it compact in some way? SO3 is a 3-dimensional manifold. It's compact, so you can actually visualize it as some sort of closed surface, but you can only visualize it if you're a 4th-dimensional being. Okay, if you go to 4th dimension, then you can visualize it. Okay? Other than that, you cannot visualize what it is, okay? Because it's a 3-dimensional surface. Okay? It's a three-dimensional surface. You can only look at two-dimensional surface because you're a three-dimensional being. Okay, so unless you plan to go to bump up your dimension, you cannot visualize it. So SO3 here, this is as a curve on it. We called it the curve itself. We called it gamma r, and gamma r will map any t to some r t. So at this point, for example, this is the point RT. So this is for some t, again, 0, 1, 2, A, B, C. And then there's the tangent space to this point. This has a vector space. And then the tangent to this point that lives in this space is RT dot. It's tangent to the space. It's tangent to the surface. Oh, okay, I see your point. What I drew here, SO3, I do it as some, again, I assume, so the intuition behind this picture is that I assume that I'm looking from an n-dimensional point of view. If you look from an n+1 dimension point of view, is that correct? Yeah, that's correct. And SO3 here is an n-dimensional manifold. It's an n-dimensional surface. That when I look at it, it's some sort of curved surface in this space. Then the tangent space, because I'm in n+1 dimension, looks like an n-dimensional vector space. And the vector space in n dimension would be a plane. So again, so I'm a 3-dimension. So I assume that this is some sort of 2-dimensional surface. And then the vector space would be a 2-dimensional Euclidean space, which is just a plane. This is the intuition behind this drawing. Okay, but we're in the end we're in n+1 dimensions. Okay, so this is just an illustration. Question. This curve is a collection of rotation matrices. Each one of them is a rotation matrix connected to each other. This is rotation matrix at time 1, rotation matrix at time 1 plus epsilon, 1 plus 2 epsilon, so on until I come to the end of the curve. Okay, so this is what this means. Okay, we know what SO3 means. So any SO3 is the bunch of 3x3 matrices such that R transpose R is equal to the identity in 3 dimensions, and we have the determinant of R is equal to +1. All agree? Okay. Then how would we define the tangent space of SO3? The tangent space of SO3 at some point R, you can get it simply by differentiating this rule. Okay. This is of course possible because we're working with matrix groups. Okay, so this makes our life easier. And it's very easy for you to differentiate matrices. Maybe you did it before. But the tangent space is the set of all R dots. And they are also 3x3 matrices, but they satisfy some conditions. The conditions that R dot should satisfy should be compatible with the conditions that R should satisfy being an SO3. Let's take that condition, R transpose R, and differentiate it. Let's assume that this is a function of time, and this is a function of time, and try to differentiate this expression, okay, with respect to t. So d, let's take this one down. So d by, hope I didn't miss it. Dt. Okay, so d by dt of this expression. Anyone knows how to do it? The product rule, exactly. So this is equal to, so R dot transpose as a function of time multiplied by R plus R transpose of t, R dot function of t, okay, equal to the differentiation of the identity matrix. What's the differentiation of the identity matrix equal to? Equal to 0, the 0 matrix, right? Because the identity matrix is a constant. So if I differentiate all of its elements, what do I get? With respect to time, I get 0. So this is in the end equal to 0. In other words, what you see here is precisely this idea of the compatibility between R dot and R. So if R has to satisfy this constraint, then R dot needs to satisfy this constraint. And this constraint simply says the following. Says that R dot transpose R is equal to minus R transpose R dot. And I can write it actually differently using the fact that AB transpose, A multiply the transpose of the product of two matrices is equal to the transpose of the second multiplied by the transpose of the first. So I can rewrite this as follows. Agree? What do we call this matrix that satisfies this condition? A skew-symmetric matrix, exactly. A matrix, so this matrix that's R dot transpose R, if we take this as a matrix, it should satisfy that it's skew-symmetric with respect, okay, as a consequence of this condition that we had on SO3. Okay? So you see, now in this way we defined what the space R dot, what the space of what R dot lives in. Okay, it's a 3 by 3 matrix, but satisfies this special condition. Question? Because this expression is equal to identity. So actually, we're differentiating this is equal to I3. Okay.
Second condition will not have an effect in the again determinant of R.
Good question. I don't think so. I don't think so. Because what this condition does is that this condition alone gives you two possible solutions. Okay, one that is right-handed and one that's left-handed, which includes the reflection. This one excludes the reflection. That's what it does. Okay. Do we have here the same? I'm not sure. I haven't thought about it, but at least that's what we will need at least. Okay. Any question? We said that there is a name for the collection. You see, something important to note, that this tangent space here, the one in green, so this one is the space TRSO3. How many special ones, how many ones does the manifold SO3 have of these tangent spaces? Infinite, right? Okay. In the end, it's the same number as the number of R's that it has, right? The number of points that it has. Because at every point, I have a different tangent space. Okay, they are all tangent to the surface in this point. So the collection of all of these spaces together is usually denoted like this. It's the TSO3. Okay? Whenever we write it like this, we mean this is a set. It's like it's a manifold actually. It has all of the points along with all of their tangent spaces. Okay, and usually an element of this would be denoted by R dot. Okay. The bottom line of what this says is that every R dot has to have the information of its corresponding R. You cannot talk about the rate of change of a position in general. This is the point here. So this is the rate of change of an orientation. If I cannot tell you what the rate of change of the orientation is, okay, you cannot use this information unless you know what R is. Okay, at this instant in time. So they are coupled together. The picture here is that R dot is a tangent space to SO3 at that point R. Okay? So that's why they are coupled together in this way.
I think here, should it be R dot R transpose, or from here it should be R dot R transpose, I think.
R dot R. That's correct.
It is negative of R transpose R dot. So the transpose should be R.
So the transpose of this one will be R transpose, R dot, transpose, which is R dot.
Oh, okay.
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 This R belongs to have the structure of the vector space or the
No.
white belong to space or
This one. This is another manifold that's known as the tangent bundle. I just write it because it's very famous. Okay, and we don't have time to construct it and talk why is it a manifold, what the dimension of it, and so on. It's a good point. Leave it like this, because we need really a lot of construction just to tell you why this is the case. I'm just writing like this so that whenever you see it, you're gonna find these pair together, they live in here. And I don't mean here that this is the product space of this SO3 with the tangent space. This doesn't, what does it mean? Okay, but keep that there just in mind. Whenever you see the tangent bundle, this is the manifold they're talking about. Okay. Can you get? R. By integrating. But what is integration? Very big question. Later on, we're going to talk about. What is integration? Of course, you know what integration is, but what is integration on a manifold? A big question. Later on, we're going to look at it. A Lie group has a special space, has a special, one of these elements is special. What is it called? The identity element. One of these points here, one of these R's is very special. Okay, I don't know, maybe it's this point here. Again, this is just an abstract, okay, picture. So this point, okay, keeps on. So this point here is the identity in 3 dimensions. It's the identity rotation. What does the identity rotation mean? No. We're at the same orientation of the reference that we chose, right? So the relative orientation between this body, okay, for example, what this R represents, that represents the orientation of, course, with respect to some reference frame, is identity, means that they have the same orientation, okay? So this element here, it has its tangent space of its own. And this tangent space is the tangent space to SO3 at the identity. Okay? But you see, it's independent of any R. It doesn't have any information on R here. And it also has some vectors. Okay. Hope I'll try not to do that again. So it has also some vectors of its own. Let's see, what do these vectors, what structure do they have? So we saw that this is what the structure of TR-SO3 looks like. If we plug in R to be the identity, so TR at the identity, so the tangent space at the identity, what does it look like? Is the set of all matrices. We're going to be calling these matrices a very funny name. We're going to be calling them omega tilde. That's just the name of the matrix. Just like here when we call this R dot, is the name of the element. Here is also the name of the element. It's an element of R 3 times 3, so it's a 3 by 3 matrix that needs to satisfy this. But here the R is equal to what? To the identity. Okay, so what happens with matrix multiplication? It just disappears, because the identity multiplied by any matrix is the identity. Identity multiplied by any matrix is, identity multiplied by any matrix is the same matrix. And we called here, instead of R dot, we called the elements of this space omega tilde. So elements of this space have this nice property. And they are the space of what? What do we call the space of? The space of skew-symmetric 3 by 3 matrices, exactly. So the tangent space of SO3 at the identity has this very special structure. And we give it this special name. We call it small SO3. Okay. Small SO3. So we have big SO3, capital SO3, which is the Lie group. And this is small SO3, which is the tangent space to SO3, to the group, to the Lie group SO3, at the identity, which is a special element that this group has. And it's called the SO3. And it has a very special name. And also it has a special structure. First of all, is it a vector space or not? Why? Because all tangent spaces have this structure. Okay? All tangent spaces have this vector space structure. Again, the first thing that comes into your mind when we talk about the vector space structure is that what? If I give you 2 omegas, 2 elements of this, you can add them or not? Yes, you can add them and you get the same element. You get another element that's skew-symmetric. If I give you 2 elements here in SO3, and I tell you add 2 rotation matrices, do you get another rotation matrix? No, because you don't have a vector space structure. The first thing that vector space structure violates is the addition. So this is a very special structure, and this is also a very special space. And every Lie group, okay, every Lie group has something that looks like this. not necessarily skew-symmetric matrices, but it has that the tangent space at the identity is always special. And usually this space is called the Lie algebra of the Lie group SO3. Okay, so small SO3 is the Lie algebra of the Lie group SO3. The term algebra itself is something that has more structure than a vector space. Okay? An algebra is a vector space plus some extra operation that people call vector multiplication. The most famous one that you know about is 3 dimensions, R3, and we make it into an algebra by giving the cross product. So the cross product on R3 takes one vector, another vector gives you what? A third vector, okay? So this third vector, which is the cross product of 2 other vectors in R3, by the way, cross products only work in R3 because only R3 can be made into an algebra. Try to do it in R2, it doesn't work, or in R1, there's no such thing. So this is only in R3. So this Lie algebra of the Lie group, okay, is because it has this extra structure. We won't be needing it now, but again, just so that you know that the term sticks to your mind. Yes, Mohammed. R3 only. Only R3 that has this algebra structure. Okay. So now the question is the follows. So omega hat, no, it's not here. So omega hat is a vector here, and r dot is a vector here. Is there a relation between both? Can we map tangent spaces to one another? Or in other words, can we map even this R to another R here? If I give you 2 R's, can you make another R between them? Does the group has this operation? Yeah, the group operation. The group operation takes 2 R's and gives you a third one. You can always do that. And there are different ways where I can use this group operation. The first one is the following. For any R, okay, so if I choose some R, a special one that's an R SO3, I can define 2 maps. The first one is called the left translation. It has nothing to do with translation as in, okay, moving around in Euclidean space. This is just the name of the map in general, abstractly. It's called the left translation, and it's defined as follows. It's defined as L R, so it depends on the R, okay? So I need to know the information of the R, and it takes one element from SO3 to another element of SO3, okay? I might give it another element. Let's call this other element, R, I just want to use something that will not violate what we're going to be talking about. So R bar. So R bar is another element. And the LR map will map this R bar to the following. We'll map it to this one. Okay. It will take R and apply the group operation between this R and the R bar. Okay. And I can define it in another way. I can define the right translation. Which is R. Again, now here's just a notation, abuse of notation. So the R down there, we're going to make it bold R, okay? Just to differentiate it between, okay, we actually have colors here, so let's use colors. Let me go back. Let's change this R to be colored. This one. Then we have here the R, which is a map SO3 SO3. It will take some R bar and it will map it to Is that clear for everyone? By the way, I didn't introduce any new maps. Okay, this is exactly the same old group operation that you're used to. I just used it differently. The group operation takes two elements of R of SO3 and gives you a third one. If I fix one of these slots, either the first one or the second one, so here I fix the first one, and here I fix the second one, I make a map instead of from SO3 to SO3, I make a map from SO3 to SO3. So this is exactly what this does. Okay, and you're going to see this in mathematics, okay, again and again. It's just a recurrent way of defining new maps from old ones. Whenever you have a map, okay, this is in general. So if I have a map between from space m times n to space w, whatever m, n, w, whatever space the structure they have. So from m, n, w, I can give m, n, and I'm gonna send from these spaces to some w that's defined as f of m, n. Okay, I can always make up new maps. If I give you some m, okay, then I can define fm as a map from n to w. Or if I give you some n, I can always define a map that goes from m to w. So this is something that's always general. You can always do that, okay? By just taking one of the slots and fixing it by some element, okay? Is that clear for everyone? Clear? Yes or no? Want to repeat? Yes, okay. I have a map, okay? I have an operation that acts on two elements, okay? Of any space, two vector spaces, or two manifolds, or two groups, whatever. For you to define this f, you need to provide to me one element in m and one element in n, right? And then f would eat these two elements and give you some element in w, okay? Let's actually try to make it easier, just to make it clearer. Let's make this w in this space w something in r. Okay, r. Okay, so you see I have a function that takes x and y, for example, and gives you r. So it's a function of x and y. If I choose one of these elements, one of these x's to be fixed, okay, you see here, this is what this means. I choose one of these elements to be fixed, then I have only the y that's changing, right? Then I have a new map that takes only elements from n that goes to r. By only fixing that, like this element is fixed in this map. And in the second case, I fix the second slot and I only enter something in the first slot. This is what happens here. Okay. So I just define two new maps from the old group operation that you're used to. So the group operation takes two elements of SO3 like this. If I fix one of these R's, then I have a map that goes from SO3 to SO3. Okay. The interesting thing about this map, okay, and this is something we didn't discuss, this is in general between maps, that I can, if I have something that goes from this manifold to that manifold, I can use this to define something that goes from tangent spaces to this manifold to tangent spaces to that manifold. Okay, this is usually called the push forward map, and maybe you're used to the Jacobian. So the Jacobian of some function, okay, that goes from one space to the other, it doesn't map elements from the manifold to the manifold. It maps elements from the tangent space to the tangent space. The manifold, the Jacobian maps tangent vectors to each other. It doesn't map points. Okay, but we will not go into details from here. The only intuition that I want you to get out of this is that if I have this picture at r dot lives here with some point r, and I have the identity element with some vector omega tilde, then I can take this r dot and I can map it to omega tilde, so that this is what they are related, how they are related, and they are related by the tangent map or the push forward of these two maps to each other. Okay? Because the element here that I can go to can be the identity. Okay, the identity is one of these elements. You agree? So I can fix one of the R's. So this is what I'm gonna do here. And I can map to the identity. And this is how I can go there. This is a lot of abstraction, but in the end, what it happens is mathematically is very simple. This is what happens mathematically. So the tangent, so again, the velocities at SO3, at the Lie algebra. So if you multiply R dot by, from the left, by R inverse, okay. If you multiply R dot by R inverse, where do you go? Think about it. R dot lives in the tangent space of R to SO3. I can map it by R inverse. If I multiply R inverse by R, where do I go? To the identity. You all agree? Multiplying from the left or from the right, R by R inverse, I go to the identity. So multiplying from the left the tangent vector to R takes me to the tangent vector at the identity. Again, okay? So R inverse multiplied by R takes you to identity. R inverse multiplied by R dot takes you to the tangent space. Again, so will take us to something that lives in the tangent space at the identity. Okay, because this took us at the identity. This is the intuition of that, okay, the picture I just drew from before. Mathematically, what this will give us a skew-symmetric matrix. Okay, if we go back to the condition that we had, of course, R inverse here is simply R transpose. So let's just use the transpose. So R transpose multiplied by R dot has to be a skew-symmetric matrix from what I showed you earlier. And this will be equal to the omega we're talking about. I can post multiply R dot by R transpose, and I'm gonna get another omega tilde. So this is omega tilde 1, omega tilde 2. Both of them are at the algebra, but they have different meanings. Okay? Now let's put some indices and everything will be clear. Okay? It's natural that you're all confused. With some indices, everything will be clear now, hopefully. Let's assume that we have the following configuration. We have some frame, we call it frame S, and we have another frame that's attached to the same point. We call it the frame B. So B is a rotating frame, so it's moving, and S is a stationary frame. So we're going to represent the configuration of B with respect to S by some rotation matrix, and it's changing in time. Okay, so it's changing in time. So there is also a rate of change of this. Okay, this is a 3x3 matrix, and this is a 3x3 matrix. If I post multiply R dot, which is BS, by SB, and RS down B up is the inverse or the transpose of RB with respect to S. Everyone agrees? Again, RB down S above means the rotation of frame B with respect to frame S. The RS down B above means rotation of the orientation of frame S with respect to frame B, or the inverse of frame B with respect to S, or the transpose of B with respect to S, right? The inverse is the transpose of B with respect to S. Okay? So what I wrote here is this part. The result is some angular velocity matrix that is B with respect to S expressed in B. This is a skew symmetric representation of what we're going to call the angular velocity. So this is the angular velocity you're used to of frame B with respect to frame S expressed in frame B. Let's play the other way around. Let's take a look at the second one. So R B S dot multiplied by, from the right, by RSB will give us omega B with respect to S expressed in S. The first one, you can read it as follows. It is the angular velocity of frame B changing with respect to frame S expressed in the frame B, which is the moving one. The second one is the angular velocity of frame B with respect to frame S. So it's the same motion. This is important. When these two are the same, we're talking about the same thing, the same motion. But the numbers, of course, are different, right? Because one of them, I'm looking at it while rotating with the body. These are numbers I get while rotating with the body. The other one are fixed. Okay? Who here is familiar with the term gyroscope? Gyroscope. A gyroscope measures what? No. No. What? No. Gyroscope. Gyroscope. What does a gyroscope measure? Angular velocity. A gyroscope measures angular velocity. Which one, if you look at the numbers that you get from a gyroscope, which one do you think it's measuring? Is it that one or this one? The body frame. A gyroscope always measures the angular velocity with respect to some fixed frame that you have. You usually calibrate it. And then you represent this number into the body frame that's you're rotating with it. Okay? So the gyroscope measures this quantity. If you want to get this quantity, you need to always you need to measure it from something that's fixed, not something that's rotating. So you need to look at the body that's moving from something that's fixed. So if you have some image processing module that's looking at a body while rotating and is giving you these values, which one will you be measuring? The second one, because it's in a fixed frame that's not moving with the body. So that's the intuition behind it. So this observer is fixed, looking at something that's moving. This observer is moving with the same body and is trying to measure the relative angular velocity with respect to something that's fixed. Clear? Okay. Yeah.
So when talking about the elemental SO3,
At which SO3? Big one or small one? Big one. Rotation matrices. Okay. Yes.
A vector at a particular point on the manifold SO3.
A vector at SO3? What do you mean by that?
Vector at a point on the manifold SO3.
Okay. A tangent vector, you mean?
Yeah.
Okay.
So we represent it with dots.
Yes.
In terms of differentiation, sorry. But if, say, for example, we've taken into consideration the fact that this manifold contains an identity element itself.
Yes.
How do we dot the identity element?
You don't. You don't. And that's another question. Okay, that's another confusing question, but that's a fact. Who here for the people who use the gyroscope, okay, or in general, you're all familiar with the angular velocity, right? Angular velocity, everyone familiar? What is the integration of the angular velocity? What do you get? Completely wrong. Completely wrong. There is no such thing as the integration of angular velocity. Okay, because integration, if we go back to this picture, integration means I need to move along this curve. I need to take a tangent vector, and then this is the r. This is the dot of some r. So this vector is the dot of some r, but this vector is not the dot of any r. It's not the dot of any I element. This is exactly the point you're making. So I cannot integrate this velocity vector. So in other words, people who ever try to take gyroscope measurements and try to integrate it, they will get garbage. Nothing. Doesn't make anything. Doesn't mean anything. Again, this is precisely what all of the confusion we're trying to make here in the course. Velocities are different from the rate of change of some displacement variable. Okay? So these are what are called velocities, elements of the identity, elements of the algebra, while the rate of change of some variable in general lives in the tangent space. The reason why you're always familiar that both are the same is that you've always worked in Rn. When working in Rn, then the tangent space at the manifold Rn is always Rn. That's why you always think of the position as a vector, the velocity as a vector, force as a vector. Everything is nice as vectors and everything works nicely. And this is where everything fails. This is where linear algebra fails. Because position is a point on a manifold. The rate of change of position is a tangent vector at the tangent space to this point on the manifold. And velocity is an element of the algebra, because this is a Lie group. Okay. Hopefully this will make sense. Again, when you start making calculations, things will be clear. Let's finish up this part and then I can take more questions. 1 second. Because the last part that we're gonna finish is, this is what's the dimension of this? 3 by 3. Dimension of that, dimension of this, but skew symmetric, right? A skew symmetric 3 by 3 matrix, how many degrees of freedom does it have? How many independent numbers can you choose? Only 3, exactly. You've seen before that as 3 by 3 matrix, in general, I can write it as follows. I can write it as omega 1, omega minus omega 1, omega 2, minus omega 2, omega 3, minus omega 3. You've seen that before, right? Which means that if I give you some element in SO3, you can easily give me what? An element in R3, absolutely. So we call this what? This map, we call it what? Bijective, right? We call it a bijection because if I give you this matrix, you can give me 3 numbers. If I give you the 3 numbers, you can put them in matrix form. Okay? So if I can take this matrix and I can give you some vector in R3, and I'm going to call this vector omega, and it will have 3 numbers, omega 1, omega 2, omega 3, which are simply, if I give you this 3 by 3 matrix, you're going to take second column, third row, put it here. First row, third column, put it here. Second row, first column, put it there. This is the map. It's a map, right? Between 2 spaces, and it's as simple as this. It's not. There's no addition, no multiplication. It's just a map that takes matrices and gives you R3. So in the end, by taking this map, we're going to be calling it S, and this S will take an element in R3, and it will map it to small SO3 by taking any vector in R3, any vector omega, and sends it to its corresponding skew symmetric matrix representation. The skew symmetric matrix is even much more deeper than that. It's not just some trick. It's something related to actually the vector product, the cross product. And this is something that you can prove, you're going to be proving in the homework, that if I give you some X and some Y in R3, and you take the X, the first one, the first number, the first 3 numbers, the first vector, and you do a skew symmetric form of it, so you make it into a 3 by 3 matrix, and then multiply it by Y, you're going to get the same number or the same vector that corresponds to X vector product Y. Okay. So this is much deeper than just some trick that picks an R3 to put into a skew symmetric matrix. So again, just to conclude, R is a point on the manifold, corresponds to the relative orientation of some frame with respect to another frame. Okay. Here, I choose the R to be the frame. Again, we're talking about some body fixed frame attached to some drone, some robot, some end effector, whatever, relative to some relative reference configuration. Okay. This is when both of them are aligned together, then this is the identity element, then R is the identity. It's changing with time, so it has some sort of time derivative. This time derivative is another 3 by 3 matrix, okay? But it's looking at it abstractly, it's a tangent vector at some tangent space to SO3 at the point R, BS. Then by left multiplication or right multiplication by the inverse of this R, I can map this tangent vector to another tangent vector at the identity element, because this is a Lie group and it has this special identity element. And the identity elements here are skew-symmetric matrices. And because I have these skew-symmetric matrices, I can represent them by some element in R3. So I can represent this by the S inverse map. So S takes R3 to SO3. The S inverse would take you from SO3 to S, which is this idea that I told you, take the first, second column and blah, blah, blah. So S inverse will give you some omega B, BS, and this will take us by the S inverse to some omega B, S, S. And this is what we call the angular velocity between quotes vector. To be continued, inshallah. Okay, let's stop here. And I can take any questions, okay, for people who want to leave.